Why hello, I am Oro, and this is a short and simple presentation on how to do planetary motion. And if you take a look at this objectively, maybe from a few yards back, you'll see that it also applies to motion with cogs or other forms of machinery. And just to help set the scene a little bit easier, I'm using a default starry background from Bryce 6.3. This equally applies to Bryce 7, and the ground plane, the default ground plane I have there, is set to invisibility. The only reason that's there is that it gives me an idea of coordinates. It gives me a nice, simple, easy graph that I can see in wireframe. So there are two dimensions in this that make it both simple and complex. The simple bit is that we're talking about straight circular motion, so we don't have to deal with Kepler's laws, acceleration, deceleration, or ellipses. A complicated situation is that we're looking at one planet orbiting another, and then a third planet orbiting the second at an angle to the ecliptic, or to the equatorial plane of the first. So we have three spheres set up. This is what I call a two-arm animation, because we have one arm set up between the big one and the middle one, and another arm set up between the middle one and the little one. So we're going to take this exercise in basically 4 levels. The first is setting up the model. The second bit is parenting the model, creating the relationships between the parts. The third bit is timing the system. And finally, the fourth bit will be colouring in the planets. So let's take a look at the first system. We're just setting up the model. Take it very easy. We've got 3 spheres in alignment horizontally. Keeping everything at 0, 0 is just a very good modelling technique, so you can understand where and when everything is happening. Now in this situation, we're going to be doing 2 different types of orbital speeds. The middle planet has to go around the large planet in one orbit. In that time, the very little planet has to go around the middle planet 3 times for every main orbit. So once we've placed the spheres, we're just going to parent up one sphere to the controlling sphere. So middle one is parented to the large one, little one is parented to the middle one. We're propagating all the measurements in each sphere. And we're going to add that last complicating factor right here. We're tilting the last arm at an angle to the other ecliptic, or to the other equatorial plane. Using the information center down below left, we can see exactly how many degrees we want to tilt to the plane. So let's move along to the timing of the system. Now, as you recall, for one full orbit of the middle moon, we need 3 mini orbits of the satellite about the moon. Now, I don't know how long my finished use of this animation will be, but what I want to do is create a small subsection that can loop, and I can drag out the animation for as long as I need it. Now, a good number I like using is 12. It's divisible by 1, 2, 3, 4, 6, and of course 12. So it allows me to create a certain amount of flexibility and knowledge of where I am, how much I have to turn, and how long the duration will have to be. So I'm going to set this duration to 12 seconds, which means one full orbit is going to be 12 seconds, and each mini orbit of the second arm will take 4 seconds. One technique I like using is dividing a full 360 degrees into 3 parts, so each part is 120 degrees, because it's just one easy number to remember. Once again, using the information center at the bottom left is a great way to gauge just how far I've turned. For the second arm rotation, the best bet is for me to work in object space. After that, it's just a matter of working out the time of how many orbits I need to make. So if each orbit needs to take 4 seconds, 1, 2, 3, then each step will take 120 degrees at every 2-second point. It's about now that all you smarty math dudes out there are thinking, well, every 2 seconds, it's 123. That's only 2 full orbits. And that's true, but of course the third orbit comes from the combination of the middle moon orbiting around the large one. When we finish, we'll play it through and you'll see 3 orbits going around the moon. Well, that's our main motion sorted. The final step is, of course, colouring the spheres. But rather than colour the spheres that we see here, what I'm going to do is add more spheres over the top of the ones we have. By doing so, we'll have independent control over the materials, and they don't have to spin at the same time as the planets are orbiting. Moreover, if you're looking to tilt the axis of each individual planet, you can do so without actually ruining your system. So here we go. Here's a snappy alignment tip you might want to take on board. By locking what I call the string or robotic spheres, and by selecting both the string and the planet sphere it's meant to control, you can align them together and only the planet will go to the string. If you want both arms to be off horizontal, you can change the main sphere and its 4 keyframes for the full orbit, or simply bank the camera. To make the entire system loop over your 12-second cycle, get into the AML, select your system components, and shift select the names that you want looped. So by using this system, you've got a robust orbital system in place, and you can add extra keyframes to the shell or to the material spheres, so you can tilt the axis, orbit them at a different speed to the full system orbit, and generally have better flexibility on how your system needs to be aligned. Final considerations: if you're outputting to video or to web, try looking at your frame rate, altering it to 24, 25 or 30 frames a second, or increasing your document size to standard DV or HD.